carbonic acid is formed, and this acidic water then seeps further down into the carbonate host rock through fissures and cracks in the host rock, and dissolves calcium carbonate from the host rock. And in the last stage, the same solution, which is up here with a high PCO2, enters the cave system, which has a much lower PCO2 than above the cave. So the CO2, the excess CO2 from the solution can rapidly degas from the solution. The solution gets supersaturated with respect to calcite, and eventually you get the formation of all different kinds of speleothems. So the first step is the dissolution of CO2. So as I told you on the slide before, you have a relatively high PCO2 in the soil zone, which is orders of magnitude higher than in the atmosphere above the cave. And this is mainly due to root respiration, and high amounts are produced by soil bacteria. And the production of CO2 in the soil zone strongly depends on the temperature of the soil and the water content. And of course, so at high temperatures, the production of CO2 by the bacteria is relatively high. So you find up to 11% of CO2 in the soil zone in the tropics. In the temperate regions, it's up to 6%, and in the cold regions of the tundra, it's much lower, only up to 1%. Okay, so what happens when the water enters the soil zone, where you have the high PCO2 values? So the CO2 is then dissolved in the seepage water, and this can be described by Henry's law, which is that one here. So basically, this is the Henry constant times the partial pressure of the gaseous CO2 in the soil zone, and this gives you the concentration actually of the dissolved, or the partial pressure of the dissolved CO2 in the solution. And the important thing to know here is the solubility of CO2 is higher for lower temperatures, which means so if the temperatures are lower, you can in principle dissolve more CO2 in the solution. This is what's shown over here. Okay. So once the gaseous CO2 is dissolved into the water, it reacts with the water and forms carbonic acid, which is shown over here. So basically, you have diffusion of CO2 into the solution, and then you have a conversion reaction with the water, and that forms carbonic acid. And this is just the reaction constant for the formation of carbonic acid over here. But also important to note is that only 1 per mil of the dissolved CO2 in the solution is actually carbonic acid. So most of the CO2 will stay just aquatic CO2, which is sometimes neglected in some models. So it would better be to state the whole thing like that. So you have like a concentration of CO2, which is just the sum of the dissolved CO2 and the carbonic acid. Okay. So once the carbonic acid is formed, it will dissociate in different stages. So the first stage would be the formation of hydrogen ions and bicarbonate, which is with a reaction constant which is usually stated as K1. And in the second stage, the bicarbonate will dissociate to hydrogen and carbonate ion, which is described by this reaction constant. And the total amount of dissolved carbon in the solution is just the sum of all different species which are involved in the carbonate system. So this would be the dissolved CO2 and the carbonic acid, the bicarbonate and the carbonate. And which species is dominant in the solution is strongly dependent on the surrounding pH values. So for very low pH values, like acidic water, the dissolved CO2 would be the dominant species. And as soon as the pH value rises, the bicarbonate ions will be the dominant species. So for typical karst waters, the solution will be dominated by bicarbonate, as we have like pH values between 7 and 8. And for even higher pH values, the carbonate ions will be the dominant species in the end. Yeah. So this is just again the overall reaction. So what I showed you before. So you have the dissolution of gaseous CO2 in the water, and then all the different reaction constants, which are dominant, like dependent on the surrounding pH value. Okay. So what happens then during the dissolution of calcium carbonate? So if you just would put calcium carbonate in water, it would also dissociate to a certain degree. So this is described by this reaction constant. So basically you form calcium ions and carbonate. And if you would consider all the reactions I showed you before, in the case of chemical equilibrium, the concentration of all species could in principle be calculated. And so this is basically what is shown over here in this table. So these are the different reaction constants for the different temperatures. And what we can learn from that is that if you have like higher surface temperatures, you get higher CO2 values in the soil due to the higher productivity of the soil, and also higher dissolution rates of calcium carbonate, despite of lower solubility of CO2. But the CO2 will be very, very high compared to cold regions. And of course, the concentration of calcium ions inside the solution will also be higher at higher temperatures. So this is a plot which I took from Baker et al. 2016. So this is basically the trip water concentration of calcium in different solutions of cave waters from different regions, from different climate regions, plotted against the mean annual temperature. And what you see here is like maybe a general relationship with temperature, but there are obvious several other processes which could control the calcium content in the water, which plays like a major role in the dissolution of calcium carbonate. And so one of the important things is the open or closed system conditions. So open system conditions would mean that all the three phases would be in equilibrium, and they had like unlimited time to equilibrate with the PCO2, and the PCO2 remains constant. That means in particular that during the dissolution of calcium carbonate, because during the dissolution of calcium carbonate, the CO2 will be consumed from the solution. Additional CO2 from the soil is provided to the solution through cracks, fissures, or due to high porosity. This means so the overall reaction would be so like these are like this is the summary of all the equations I showed you before. So you have like CO2 in the water, you have water and calcium carbonate, and if the pH value is low, the reaction is going into that direction. So you have the formation of calcium and two bicarbonates. And like an example for that would be like a puddle of water on top of a limestone with a PCO2 of, for example, 360 ppm, which is like a little bit low because the atmospheric pressure of CO2 is much higher now, unfortunately. But so just for the example, so the dissolution, so the potential of the dissolution in equilibrium with this PCO2 would be 55 milligrams per liter. Okay, and the opposite would be the closed system conditions. So in the closed system, all these three phases, like solid, liquid, and gas, are not in equilibrium. That means that during the dissolution of the carbonate, the CO2 from the solution will be consumed, but there's no connection to the soil zone. For example, like in a water-filled fissure, or due to very low porosity above the limestone. And then you can take exactly the same example. So you have like water on top of a limestone and the same PCO2, which I showed you before. But the capacity to dissolve the carbonate host rock is only 25 milligrams per liter for this case. So that means that only 40% of the amount can be dissolved, of the amount I showed you before can be dissolved in an open system, right? so it's much lower. But as always, like in a natural system, most systems are likely to be between an open and closed system, or like depending on the season, it can be open and closed. It just depends on like the coverage of the host rock, right? Okay, so the closed system conditions are probably important for low temperature conditions. So this could be in the case of poorly ventilated soil, very humid regions, or even very cold regions where there is no equilibration between the gases and the dissolved CO2 possible. Okay. Another maybe very important point for the formation of caves is the mixing corrosion. So this is basically, here is a comparison between open and closed system again. And what you see in this plot is like, this would be the partial pressure of dissolved CO2 in the solution. And in this area, plotted against the equilibrium concentration of calcium carbonate, which means like what would be the equilibrium concentration if all the CO2 is consumed from the solution. And under open system conditions, so there is like an open space between the CO2, you would like have away from like that would plot along this line. So for two different temperatures, for 10 and 20 degrees, and for 10 degrees, you would end up with a concentration of somewhere here between 4 and 4.5 moles per cubic meter, whereas the CO2 in the closed system is consumed constantly, and you end up with a much lower concentration. And if you would have like a solution, like if you had like a stream or something, or like a fissure or a crack which goes together above the cave, and you would have a mixture of both solutions, so the open system solution and the closed system solution, and you would mix them like by 50-50, you would end up with a solution which is then again undersaturated. So the capacity to dissolve carbonate from the mixture of the solution is then higher, right? So this is maybe a point where you can like form like bigger chambers or something like that. Okay, but there are also many other factors which could potentially influence the dissolution or the capacity of dissolving calcium carbonate from a host rock. So I'm trying to walk you through this a little complicated picture over here. So just very quickly. So this would be the temperature effect from an ideal open system, so with a PCO2 of, so this is again, it's again a bit old picture because it's just 300 ppm, and then, or like 3,000 ppm, like 0.03% of CO2. So the capacity to dissolve calcium carbonate would be 55 milligrams per liter at 25 degrees, and when you change the temperature, so the capacity to dissolve calcium carbonate will increase. And this is what I basically talked about before. So if you just increase the PCO2, you have like a boost of dissolving conditions of calcium carbonate. So this would be what I talked about before, that's the mixing corrosion, which can increase, can be a boost of like 10 milligrams per liter per 0.5% of CO2 indifference. And there are also other processes like organic compounds, which can like really boost the dissolving conditions. But this is also in independence of the oxidizing compositions of the organics. And I'm not an organic guy, so this is just like for completeness mentioned over here. Okay. So to sum up the dissolution processes, the individual processes in the karst and the soil are relatively well understood, but it's a very complex system. So the natural system is very complex. So it's still very complex and challenging to really model drip water calcium, because there's also like a high spatial variability from site to site, and also potentially very high temporal variability at an individual site, like inside a cave. The conditions can also be very different for different trip sites. Okay, so what happens during the actual formation of speleothems, precipitation of calcium carbonate? So if the drip water, so all the processes which I just described before, so the acidic water seep through the carbonate host rock, it dissolves carbonate and is in equilibrium with a very high PCO2. If this solution then enters a cavity or a cave system where you usually have like much lower PCO2 values, you get degassing of the excess CO2. And that means the pH value will rise, you get supersaturation with respect to calcite, and then you have the formation of all kinds of speleothems, like stalagmites. But usually we are interested in not in the stalactites, but also particularly in the stalagmites. So if the solution drips down to a stalagmite, it forms like a very thin solution layer. It's about 1 millimeter in thickness. So the degassing of the excess CO2 will be very, very fast, like in the range of a few seconds. And then the pH value will rise, and then you get supersaturation and precipitation. So this is like again the scheme which I showed you before. So far, I just told you about like all the reactions which were going on. But for the formation of speleothems, the individual rates of the reactions are important to know. So because there are very different time constants for the individual reactions. So some reactions is just like the diffusion of some ions from the gas into the water and inside the water itself. And some reactions are very slow. For example, the conversion of dissolved CO2 into the carbonic acid is a slow reaction, while the dissociation of the carbonic acid into hydrogen and bicarbonate is almost instantaneous. This is a very fast reaction. Yeah, and in principle, you can see here like what happens during precipitation and dissolution of calcium carbonate. For the dissolution, for the precipitation, you would have like this reaction. So one calcium ion would consume 2 bicarbonate ions, forming calcium carbonate to the surface of the stalagmite, for example, and then as a result there is 1 water formed and 1 CO2. And this CO2, which is formed during the reaction, would need to be transferred like out of the solution again. So as long as you have precipitating conditions, you have production of CO2 and the CO2, so you have all these reactions going on, and you have to remove the CO2 from the solution to keep the solution supersaturated with respect to calcite. Okay? And so a lot of these things, like most of the things, has been done by Wolfgang Breitbrot and colleagues. And what they basically did, they calculated the calcite dissolution and speleothem growth rate based on the work by Plummer et al. In 1978. So this is just considering of all the reactions which are taking place in the fluid, like the fusion, the dissolution, and the precipitation. And all the individual reactions which are going on like at the same time, they have all different reaction rates, which are like the mass determined by the mass action law in particular. And so the PVP equation gives you this lengthy equation, which would be the rate of precipitation and dissolution. So the first term here is the dissolution capacity, or like dissolution of a carbonate host rock, and for the speleothem growth, the last part of the equation is the most important part. So this one describes the precipitation. So for the speleothem growth, the back reaction is actually the most important part. And what Wolfgang Breitbrot did then, so he took the PVP equation and all these reactions which are going on at the same time, which can be described by like differential equations, but he derived it like it's like a narration, which is pretty good for the deposition rate of speleothems. to one single equation. So this will be the precipitation rate for like solution films or like for water bodies, and so the alpha here is a kinetic constant, which is depending on the temperature and the thickness of the water layer above a speleothem or above like a horse rock or a flowstone or whatever. And so the C's here describe the concentration of calcium carbonate inside the solution, like dissolved calcium in the solution. So this one would be initially the concentration when the water enters the cave, like the maximum concentration in an equilibrium with a high PCO2. And the second one is the concentration of calcium in equilibrium with a cave PCO2, right? Which is usually much lower than the water which enters the cave. And in these plots, they show basically so the deposition rate independence of the concentration of the solution for different film thicknesses. They've done it for two different like stages. That would be just a stagnant film, which is like just laying on top of a speleothem. And they also did it like for a turbulent flow, like with a boundary layer, just a flowing solution, and then the precipitation is going on in the boundary layer on top of the speleothem. And yeah, so you see you get like very different deposition rates for different film thicknesses. But at that point, it is important to know that this kinetic constant for the case of like classic speleothems, where you have like very thin solution films, is almost independent on the film thickness. Like for the range which you find like on the film thickness, it's only dependent on the temperature and not on the film thickness, because the diffusion is very fast in like a thin layer. Okay. So yeah, I thought that would be worth to be mentioned. So what Wolfgang Treibroth and others also did say, they tried to model the shape of speleothems, like, but they had to take like a few assumptions for that. So the first assumption would be that the stalagmite is axially symmetric, and they used for the next slides I will show you, they used the stagnant film model, which means that the solution is only moved by the next trip. It's basically a stagnant film, and then you get a new drop, and then the solution is replaced by the new drop. And the other assumption is that the growth is perpendicular to the existing surface, and that the growth rate is largest at the growth axis and decreases exponentially to the edges. Okay? And if all these parameters like cave temperature, soil and cave PCO2, drip rate, film thickness, and so on are constant, and equilibrium state is established within that film. So these are the assumptions for this model. So, and this is what the model then looks like. This is a paper from Kaufmann in 2003, I guess. So, so the growth is perpendicular to the previous layer. So that means like they divided it into different boxes, and you have like the growth perpendicular to the previous layer, and the distance between these 2 points are determined by the growth rate. And the growth rate, they derived it like that. So that would be the growth rate, the maximum growth rate at the growth axis over here, and then you get like an exponential decrease with the length of the layer and the so-called equilibrium radius of the stalagmite, like just like the radius of your film. Okay, so I just want to mention that I'm going over that rather quickly. So this is the equation for the maximum growth rate. It's a bit lengthy and looks like pretty much complicated. But in principle, you have the dependence on the film thickness. The delta D would be the individual drip interval. There's the alpha, which I showed you before. That's the kinetic constant for the precipitation rate. And then you have like C and C apparent, which is in this case again the calcium content in equilibrium with the soil PCO2 and the calcium content in equilibrium with the cave PCO2. So, and if you run this model for 2 degrees of supersaturation, so you can see the dashed line would be an initial solution in equilibrium with a very high PCO2 of 50,000 ppm, and the solid line is PCO2 which is much lower, of 20,000 ppm, and then you get like this kind of plot. So what you see here is the temperature, the drip interval, and the growth rate in millimeters per year. And what you can learn from this plot is essentially that the supersaturation is the dominant parameter for the maximum growth rate. Pretty easy if you just thinking about this electric equation here. Okay. And so I was talking about the equilibrium radius. That is basically the radius which can be formed by like the solution. And this is, so they write this equation for that. So V would be the volume of the drip, which is in the range of 1 cubic centimeter. And what you can see is that the R0 is independent from the supersaturation. That this is what you can learn from this plot over here. So this is again the drip interval plotted, so the temperature plotted against the drip interval, and so these lines are the equilibrium diameters in centimeter. And you see for very high drip intervals, the equilibrium radius would be much lower than for very high drip rates. But this is just because you replace the solution like faster, so that this initial supersaturation would be just higher for like faster drip rates. Okay. So, and there were like others. They took essentially these models. So, there's the work of Mühlinghaus et al. So they took essentially the same model, but introduced a mixing parameter, which is essentially like, so what I showed you before was like that the whole drip was just replaced by the next drip, but in reality this might not be true. So so they introduced like a factor of like to which degree the solution film is completely replaced or completely lost due to splashing. So the p-value here of 0 would be the complete replacement of the existing film, and the value of 0 would be like the loss of the whole water just by splashing, for example. And then they did like these 3-dimensional plots. You can't really see them very well, I guess, but so this is the replacing factor plotted here. This is the trip interval, and this is the growth rate. And you see, so the growth rate is highest somewhere over here. So where you have like not like complete loss of the solution, no like towards the complete replacement, just due to high supersaturation, right? And this is also the same plot for the diameter. Okay, so I just want to wrap this one up. So there are several models which describe speleothem growth available, but due to the high complexity of the processes in the soil and the karst, the values predicted by the models should not be taken too seriously, because they also like model that the shape like in between like different marine isotope stages, for example, but I didn't show you that because it's very complex. And I wanted to have time for my slides as well. And but it's not possible to reconstruct past changes like temperature, drip rate, or soil PCO2 just from the growth rate and the diameter of the speleothem. But however, these relationships revealed by the models, for example, the increasing growth rate, the increasing temperature and drip rate, could still be useful in combination with all the different kind of proxies we have. Okay. And this brings me now to my main research interest. So what I'm doing, or what I've been doing the past 10 years, is I try to simulate all these processes which I showed you before in the laboratory. And this requires a very precise control of all different parameters such the chemistry of the solution, the surrounding temperature of the atmosphere, the isotope composition of the solution, the atmosphere, and everything. And this in the end enables a direct investigation of all these processes. And for this purpose, we set up an experimental system, which is essentially an artificial cave system. And this is the latest version of my lab or my experimental setup. And so what you see here is basically an artificial cave. So the right-hand side would be an artificial cave where you establish a certain PCO2, which is like in accordance to what you can find in nature as well. And there's a second box attached to it, which is the cast above the cave with a very, very high PCO2. And there we produce the experimental solution. So we dissolve calcium carbonate in water, which is then in equilibrium with a high PCO2 environment. And once the solution is established, we pump it into the cave environment and precipitate all kinds of like different carbonates from thin films of solution. And what I'm going to show you in the next slide is basically the work I did like back in my PhD. So I didn't have like big setup over here. If I find time in the end, I can tell you a little bit more about like all the surrounding instruments here. But so this is basically the work I've been done in this like artificial cave box without all the surrounding here. Okay. So this is just a quick step back because I told you before. So this is again the overall reaction during formation of calcium carbonate. And what happens in a cave system? If the water enters the cave and drips down to stalagmite and forms a thin solution layer, the first step is the degassing of excess CO2 from the solution. And this is a very fast process because the diffusion in a like thin boundary layer is very, very fast. So this will be done in a few seconds. And the next step would be the equilibration to the new cave atmosphere and PCO2 of the cave. It's basically the increase of the pH value. So when the water is entering the cave, it's in equilibrium with a high PCO2. Then you get the degassing. And after degassing, all the carbon species will rearrange to the new pH value. And in the end, it will reach precipitating conditions, and then calcium carbonate is precipitated. And all these steps take place on very different timescales, right? And yeah, so we try to simulate that in the lab. And so this is the first setup which I was working with. So we produced a calcium carbonate solution that was done by using pure millicube water. And we put like certain amounts of calcium carbonate powder in it, and then we bubbled CO2 through the water column until everything was dissolved and the solution was clear. So it was basically undersaturated with respect to calcite. And then we measured the pH value and removed the excess CO2 to reach an saturation index of about 0, because this is what we expect for a solution which stays sufficiently long above a cave. And once the solution was also in isotope equilibrium, so we left it at the experimental temperature for a certain time to reach isotope equilibrium between the water, the CO2, and the other dissolved carbon species. The solution was then pumped onto a small marble plate over here, which you can consider as like the stalactite, for example. So we got like the degassing of the excess CO2 and the chemical equilibration with the artificial cave atmosphere, and the solution reached supersaturation with respect to calcite. So we had to measure very precisely the electrical conductivity and the pH value to really get like where the precipitation process starts, right? And then the solution dropped down to a second marble plate, which was 1 meter distance of flow, and as we exactly know the time which is needed to flow down the plate, we could calculate the residence time, and then we changed the residence time on top of the lower plate by just like shifting the upper plate towards the lower plate. And we had a sample collection port within the experimental system to collect samples to measure the pH and electrical conductivity. And for sampling for the DIC isotope values as well. So, and then this was just done by adding strontium chloride and sodium hydroxide, and then that was caused the DIC completely precipitate as a carbonate, and then you can measure the stable isotope values of both the 13C and the 18O of the DIC, like whenever you want. So this kind of like freezing the isotope composition for all the different time steps throughout the experiment. Okay, so so this is basically the precipitation of like artificial speleothem calcite for a solution film of 0.0 millimeter in thickness for the 3 different temperatures, and for a solution which had initially 5 millimoles of calcium in the solution. And what you can see is a strong dependence, as you would expect, with temperature. So this is the conductivity value, and since the calcium is the only ion which has like charged ion in the solution, you can recalculate the calcium concentration in the solution. And if you plot that against the residence time, you get like an exponential decrease of the remaining calcite in the solution, or the calcium in the solution. And if you provide like an exponential fit to that, you get the time constant for the precipitation of calcium carbonate. And this equation just follows from all the equations I showed you like in the theory part. And these values are indeed in very good agreement with what Wolfgang Treibel did like back in the 80s. Okay. So this is again the picture I showed you before. That's quite a busy picture. So so during like all these chemical reactions which are going on during dissolution and precipitation of calcium carbonate, you also have isotope fractionation going on at the same time. And there are like 2 general different types of stable isotope fractionation processes. Maybe you are familiar with that. So there's the kinetic isotope fractionation, and there's the equilibrium isotope fractionation. So the equilibrium isotope fractionation would just be the removal of one type of isotope, or the preferred removal of one type of isotope, and then it's basically gone. So the flux out of the system. And the equilibrium fractionation would be like a flux between 2 different phases, and the flux out of the system and into the system is basically equal. So that would be the equilibrium state. But again, in nature, most of these processes would be somewhere in between kinetic and equilibrium, which is usually called disequilibrium isotope fractionation. I prefer the disequilibrium term. And this is just like what happens with the isotopes. So you have fractionation between all different kinds of species, between the water and between the carbonate, and between the soft CO2 and the gaseous CO2 as well. Okay. So these are now the results for the stable isotope measurements from the plot I showed you before, like for the DIC experiment for both isotope systems. So this is the delta 13C value plotted against the residence time on top of the plate, and these are the delta 18O values plotted against the residence time. And what we observed was a strong increase in delta 13C values up to 10 per mil, like the enrichment over the residence time is like up to 10 per mil for the high temperatures, and the enrichment in the delta 18O values is only up to 2 per mil. But it's still a strong isotope effect, right? So what causes this enrichment is basically isotope fractionation. So this is again the plot, but just simplified for carbon isotopes. So again, the overall reaction, so the 1 calcium ion consumes 2 bicarbonate ions, forming calcium carbonate, water, and CO2. And for the case of CO2, so isotopically, one of the C atoms will go into the calcium carbonate and the other one will go into the CO2. And these fractionation, they have different fractionation factors. Okay? And I think there is, oh, sorry. There's one thing missing in the slide, I guess. So, yeah, I can do it without it. So this is what you get if you if you take the stable isotope values of the DIC, so this is again a plot that's for 30C and delta 80 low, but this time plotted against the remaining calcium fraction in the solution. This can be calculated from the plot I showed you in the beginning. That was like the exponential decrease of calcium ions in the solution, and that would mean like here, so that would be the initial state of the solution, so there's still 100% of calcium ions from the initial solution present in the solution, and then it starts to precipitate and you get removal of calcium ions from the solution. So that would be over here you only have like 50% of the initial calcium concentration. And alongside you have the isotope fractionation for both isotope systems, and then you can perform a fit to a Rayleigh model, which was published by Dennis Scholz. And so this fit would give you the total fractionation, like the combination of the equation I showed you before. So the DIC is fractionated into the calcium carbonate and into the CO2. And then you can take this total fractionation factor to test if the Rayleigh model is suitable to describe what we observed in the experiments. And this is what we did over here. So this is basically, again, the same plot, but this time with a Rayleigh model. So this is the temporal evolution of the stable isotope values of the DIC. And then we performed a Rayleigh model, which was fed by the total fractionation factor and by the precipitation rate we got from the other measurements. And as you see, so in principle, the Rayleigh model is suitable to describe the temporal evolution, at least for the first 50% of calcium precipitation. And that fits for both isotope systems.
Nice. Can I interrupt you with this stupid question? This essentially is down your last plate.
Yeah, so this would be, this is just the residence time on top of the plate. So,
right.
That would be like the initial point, like where you have like 0 centimeters distance of flow, and that would be like approximately half a meter, approximately 1 meter distance of flow, but this shown as the residence time.
Thanks. Yeah.
Okay, and then the second step, we slightly changed the experimental system, so replaced the marble plate by a sandblasted glass plate. This is because we wanted to investigate what is going on in the precipitated calcium on top of a surface, but it's hard to scratch off calcium carbonate from a carbonate surface, and you would kind of mess up the sample, so this is the reason why we took a glass plate. And essentially we took the same solution, or the remaining solution of the DIC experiment. So the DIC experiment ran for like 1 day, and then the second experiment, like the calcium carbonate experiment, runs for like 100 hours, like depending on how much solution was left. And during this experiment, we enlarged the distance of flow by the equilibration distance. We determined on the top of the small marble plate, so we got the degassing of the calcium of the excess CO2, and then we have the precipitation of calcium carbonate. And once the experiment was finished, we took the glass plate out of the system. We scratched off calcium carbonate samples for the same distance as we sampled them for the DIC, because we wanted to know how the isotope fractionation between the DIC and the calcium carbonate develops over the time. Okay. Oh, there's quite a lot missing here. Maybe I should switch to the PDF, right? So
Do you also give us a PDF
Yeah,
version?
I think
Yeah.
that's the problem, Max. It's like the version of the
Yeah,
PowerPoint. Some slide doesn't show up.
I think.
Okay.
Just like the PDF. Can I
Just open the PDF.
I think it's open over here.
Só arrastando lá.
Pode abrir direto pro pendrive.
Não, tá perto, mas só tá nessa.
Ah, isso, puxa pra lá.
You just slide.
How do we do that over here? Like, is there like a full screen mode?
To the right, maybe the 3 dots.
Ah, yeah.
Yeah.
Okay. Okay, just running through the slides again quickly. Yeah. So that was missing, the total fractionation, but I told you enough about that. Okay, so coming back to the calcium carbonate experiments. So, see, I think I left one slide out just to stay in time, but what you see for the stable isotopes for the calcium carbonate is essentially exactly the same, like the same enrichment over time as we observed it for the stable isotope values of the DIC. And so once you got like the stable isotopes values of the calcium carbonate and of the DIC, you can compare them directly. And this is what we've done here. This is an example for 20 degrees Celsius. And what you see here is again the residence time of the solution. And the different isotope values from the DIC and from the calcium carbonate. And what you see here, these values have like a large error point. And I can explain you why, because so as I told you, we scratched off the samples for the same distance of flow. But unfortunately, like during that time, the residence time of the solution on top of both plates was slightly different. And as we had like all the precipitation rate and the residence time, we could calculate, using the Rayleigh equation, we could calculate the isotope values of the DIC for the same residence times as for the calcium carbonate experiment, and this is essentially what you see here. And then you can directly compare the DIC and the calcium carbonate. And what we observed for the carbon isotopes was quite surprising, because we observed a strong negative fractionation between the calcium carbonate and the DIC, which is like not expected by theory, because in theory, in equilibrium conditions, you would have like a small positive fractionation, which would be the blue dotted line over here. But with decreasing supersaturation and increasing residence time, the fractionation becomes smaller, like kind of approaching the expected equilibrium values. So even if you take account the large error bars over here, because so the only value which is really trustful is the first one, and the other ones are kind of calculated, and we did an error propagation to be like the most conservative way you could do it. Yes. Okay. And the same you can do the same for the oxygen isotopes, and so for the oxygen isotopes it was like the other way around. So the initial value was quite in agreement with fractionation factors which were like determined in cave systems actually. So that was this is the work of Tremaine et al. 2011. But we also see the kind of rate-dependent fractionation process. So you have the negative fractionation in agreement with the literature values, kind of. But then the solution gets kind of enriched over time, and the fractionation becomes also smaller, like going away from the equilibrium line over here. Okay. All right. Yeah, and this is the last thing I want to mention about that. So we also took water samples for stable isotope measurements of the water to be able to get an oxygen isotope fractionation factor between the water and the calcium carbonate. And this is what you see over here. This is like the summary of all the experiments we performed in comparison to the experiments which were conducted by Chris Day. For like two different PCU2s, that was like the triangles here, the field triangles are the surrounding atmosphere in the artificial cave system of 1000 ppm, and the other triangles are like the 3000 ppm. And what you see here is again that our values, like the fractionation between the water and the calcium carbonate, independent of the temperature, are in agreement with the fractionation factors which are determined in cave systems, like these ones of Tremaine and Johnson et al. 2013. But this is important to know this is just the very initial calcium carbonate on the plane, which would like be the growth axis of the speleothem. And as soon as you move away from the growth axis, or like from a flow stone, right? As soon as you would move away from the initial point, you get the enrichment of stable isotopes. But the water value remains constant, and there's not enough time to re-equilibrate the water and the DIC species. So if you would have that, these values would just like move away from that equilibrium line. And this is essentially what happens if you have like PCP above a speleothem. Like if you would have like a stalactite, and then you have like precipitation before the solution gets to the speleothem, you might get completely wrong like values. So it's very hard to determine the water isotope values from values which are already enriched. All right. Okay, so I will wrap this up. So so our experimental system enabled for the first time the determination of Theta 13C and Theta 18O of all involved species in the system. So for the DIC, the precipitated calcite, the water, as well as the CO2 of the atmosphere. So during that time we took CO2 samples and we sent them to a different lab and got the values afterwards. So we observe an enrichment in Theta 13C, a strong enrichment, whereas the enrichment in Theta 18O of the calcite is much, much lower. And we observed a negative fractionation between the bicarbonate and the calcium carbonate in dependence on precipitation rates, which becomes smaller with decreasing supersaturation, and this is a strong hint to disequilibrium or kinetic isotope fractionation processes. And the temperature-dependent fractionation between the water and the calcium carbonate is in good agreement to previously reported cave values. So the system we had during that time already pretty closely resembled a natural cave system. And I don't have the time to show you what I'm doing right now because we just essentially made it bigger, but I feel happy to talk about that like with any who's interested later on. Yeah, that's it. Thank you.
Who's older?
Now, my question is about the relative relation between carbon and oxygen.
Yeah.
So, from your laboratory experiment, which is the variable that you most control the ratio between beta 13C and beta 18O enrichment?
I would say the initial supersaturation, because the higher the supersaturation, the faster you have the initial precipitation, and the steeper would be the enrichment, right? So this.
But I mean the ratio. So let's say you have an enrichment of 3 per million carbon and 1 per million oxygen.
Yeah.
This ratio is constant, or can you change it?
I think it changes. It changes. It's not like, because the enrichment in carbon is much higher than in the oxygen. So the oxygen seems to be a little bit slower than the carbon. So it's not. I think it's not constant, right, the ratio.
But there's no, let's say, study about this statistics.
To the best of my knowledge, not. But we are working on that like more precisely now. I can, if you're interested, I can show you like the new system, which is way better than that one. I hope.
Thanks, Max. You always make my brain crumble, which I think is good, because it makes me realize I should know more. I should know more about this. But I think one of the, for me, most valuable things that you show have to do with rates. Because this is the point where I'm always lost when I have to think about this. And what I find particularly interesting is when you describe, we've used that lately, when you describe how quickly actually calcite precipitates and how much slower the entire water system reacts to that. My question, or another question I think, is about how are we going to see the effect of evaporation in decay in calcite?
That's a hard question. Because
I was hoping so.
So the main problem for that would be then the isotope exchange between the different species kind of kick in,
Yeah.
right? And so you have like during the precipitation, you have like a dominant reaction going on, like the precipitation and the fractionation of isotopes during the precipitation. But alongside, you get isotope exchange between all involved species.
Yeah.
The gaseous, CO2, the species inside the solution, they try to re-equilibrate, but the system is just, so the precipitation is just going too fast to re-equilibrate during that time. What we see indeed is isotope exchange processes with the gaseous atmosphere and the DIC of the solution. So especially for high temperatures, you can see that, so you have the Rayleigh fit, but maybe the Rayleigh fit is not the best to describe that, because at a certain point when the supersaturation is already very low, approaching the chemical equilibrium, you would get isotope exchange between the gaseous CO2 and the DIC, and then you would see something like that. So the values would be pulled back to some kind of the initial values, because the CO2 is all the same which you use for the preparation of the solution and for the gaseous atmosphere as well. But to see evaporation, it's very hard, I guess, because the time of the time scales for the isotope exchange between the water and the dissolved bicarbonates or the dissolved carbon species is orders of magnitude longer than the isotope exchange between the gas phase and the dissolved species.
I mean, that thing I realized about half a year ago, which was actually after talking to you, but I find it hugely interesting. But can I simplify it by saying, if I have my evaporation indicate on the stalagmite, my interest, of course, is because of the fluid inclusions, because I see it there.
Yeah, maybe it's...
If it happens there,
Yeah.
I do not see it in the calcite, correct?
Yes.
So if it happens in the epikarst above my hand,
You
I
might
will see it.
Yes, I would say it like that. Yeah.
Thank you. That was the thing I was struggling with. Okay.
Can I comment?
Yeah.
I think it's, you cannot say evaporation inside the cake because it's with the evaporation rate will be negative.
So,
Not
sorry.
too much. Because the cake is wet.
Okay.
Is the derivative.
Yeah.
The evaporation rate it will be almost zero.
Yeah, I know. It depends on where you are in the cave, though. If you're in the cave entrance, you're in a different situation, and then it is possible.
Yes.
Or if you have strange winter, summer ventilation changes, that is the other thing that we're not worrying about it, but we're wondering about it. And what we see in our data.
Usually that we take Speleothem and consider for study, we will go deep inside the cave.
Yeah. And then you're okay.
system.
Yeah, I agree with that. Yeah.
So important topic.
Yeah. Thanks, Martin.
Okay, quick question.
Yes, thanks for sharing. It's very interesting. I have still a question. So if I collect some dribble waters in a cave, and connect you, and I know the temperature and the partial pressure of carbon dioxide, can I use your experiment? Can I use your experiment system to form or bomb some zero-rays cassette?
That would in principle be possible, I guess. Yeah.
Okay.
So I've never done it with actual cave water, so we just artificially produce, because we need like a very precise control on the solution. But in fact, we thought about doing that as well. Yeah.
Okay.
So, but yeah, in principle, it would be possible, I guess. Yeah.
Okay, thank
But you need like quite big amounts, because we don't have like thousands of years. So you need a certain amount of solution to produce enough material to get like your analysis done. So that's the main issue. So we have to choose high supersaturations, like high concentrations of calcium carbonate, to get enough material in a like feasible amount of time. So that's the main issue. So yeah.
Thank you so much.
Okay, thank you. I'm sure if you have more questions, you can approach Max and
Yeah, sure.
coffee
I'm
break. But
happy.
I think we're ready for coffee.
Yeah, just a couple quick announcements. I think coffee break will go till 11, and if you haven't registered yet, please come see us up front. Let's thank Max one more time.